Hey everybody, welcome back to Math 30-2. We are still working on the probability unit, independent and dependent events, lesson 4. So let's get started. Now the first thing we're going to do is be talking about the definition of independent events. Two events are independent if the first event has occurred, but it has no effect on the probability of the second event. For example, let's say I had a die. Oh, that's a terrible die. Go with it. And on that, I rolled a 2 on the top there. And then on another object, I have one of those spinners. Let's say I can spin that around, and it was numbered 1, 2, 3, and 4. And notice here it is on number 1. If I rolled the die and then spun the spinner, the effect of rolling the die does not affect the probability of getting a 1 on the spinner. So these two events would be considered independent. Now, another way of talking about it often deals when we're talking about picking objects, and that's when replacement occurs. Now, those types of things often happen, like I said, with objects like cards, or maybe there are marbles in a bag, something like that. For instance, if I had a deck of cards and I said, what is the probability of finding the King of Hearts? Well, we all know that there's one King of Heart in the deck and there's 52 cards in the entire deck, so the probability is 1 over 52. Now, I'm going to put the card back into the deck, shuffle it, and say, well, what is the probability now of getting the Queen of Hearts? Well, we would say there's one Queen of Hearts in the deck and there's 52 cards because we've replaced the first card and there's still 52. So that's what we talk about when we refer to things as replacement. So we're replacing objects back into the mix. And when either of these things happen, when we have replacement or when we have events that have no bearing on one another, we can say that the probability of A and B equals the probability of A times the probability of B. And we can use the word and as a little hint. We can say and refers to multiply. Where often in previous lessons, we've talked about or, and or refers to adding. And we're going to use or a little bit later here when we talk about cases. So, and multiplying, or we can kind of say that that is synonymous with subtracting, or sorry, adding, my bad. So now that would be independent events. Now, dependent events, as you probably already have guessed, is those events that have dependency on one another. In other words, if a first event has occurred, then it changes the probability of the second event occurring. And we'll say that the probability of event B depends on whether or not event A has occurred or vice versa. And in the case as cards, for instance, we can say that events are dependent when replacement does not occur. And if we go back to our little finding the probability of the King of Hearts, and again, if we have that deck of 52 cards, we know there's 1 over 52. But let's say we take that King of Hearts and, put it out. Well, now if we want to find the probability of the Queen of Hearts from the remaining cards in the deck, there's still only one Queen, but now there's only 51 cards. So that's what we talk about when we mean that replacement has not occurred. Now, the probability of that Queen of Hearts, that is dependent on the probability that that first event has occurred. We can denote those events by this new notation here. The probability of event B happening, given that event A has already occurred. So that little notation there is just the short way of saying all that. So the probability of A and B equals the probability of A. So it's very similar to the first formula, except now our second probability is the conditional probability. And we can write it in, have it as where we write the probability of A and B in words, or we can go back to our set notation where we have the probability of A intersected with B. And again, we still have the exact same formula right here. So that's the probability of A given that B has already occurred. So let's go and look at some examples and see if we can classify if these are independent or dependent events. And then we're going to determine the probabilities with the new formulas. So the first one is tossing a head on a coin and rolling a 6. Well, these are two separate objects. We have a coin in one hand, rolling a die in another hand, and whatever happens with one does not affect the outcome of the other. Therefore, we were going to say that these are independent events. Now, because we know they're independent, we can use our formula saying that the probability of rolling a head with the 6 equals the probability of having a head on a coin times the probability of rolling the 6. Well, if we wrote this out, how many heads are on a coin divided by the total number of outcomes, so in other words, the universal for that coin, and then with the die, how many 6s are on a die plus the total number in that universal. I know that's the hard way of writing it out, but just want you to see it. So we get 1 over 2 times 1 over 6. We're going to be working a lot in fractions here, okay? So we're going to keep the fractions, and we'll change to decimals sometimes, but I want everyone to get used to working in the fractions. So we're multiplying fractions, therefore we're going to multiply numerators and denominators. So the numerator is 1 times 1, which is 1, and 2 times 6 over 12, and we're going to leave it as an exact value. So remember, rounded decimals can be exact, but often they're rounded, meaning they're not exact values, whereas fractions are exact. Let's look at the next one. So we have drawing a face card, returning it to the deck, and then drawing another face card. Well, this goes back to our definition of returning it is basically the same thing as replacement. So because we have replacement, these are still independent events. So if we are going to say what is the probability of a face card and then a second face card, we would say, well, that's the probability of getting the first face card, and then we're going to multiply it by the probability of getting the second face card. And just a reminder that the face cards are king, queen, and jack, and there are 4 suits, each with its own king, queen, and jack. So that means the probability of the first face card is 12 over 52. And because we're putting the card back, we still have 52 cards in the deck, and there's still 12 face cards in the deck. Now we can reduce these fractions down, and we are going to be getting here. Let's say that is dividing top and bottom by 4. That's 3 over 13, because there's 13 cards in a suit. And we're going to multiply that by 3 over 13 again. And that's going to give us 9 over, that's 169. As an exact value. So that one there, because it's replacement, oh, we didn't write it down. That is an independent event. Okay, let's look at the next one here. So the next one is choosing a king, not replacing it, and then choosing another king. Okay, first of all, we know now because it's not replaced that these are dependent events because the first king being chosen is going to change the total number of cards in the deck. So that second probability depends on the first event happening. So written down, if we say what is the probability of the first king and then choosing the second king, that is going to equal the probability of choosing the first king and multiplied by the probability of choosing the second king, given that the first king has already been chosen. So let's look at what we have here. Well, we can say that what are the number of kings to start with? Well, there were 4 kings and there were 52 cards in the deck. So the probability is 4 over 52. Now the second probability is going to change. That's going to change because we have already taken out a king. So the total number of kings now is only going to be 3, but also the total number of cards is going to be reduced to 51. So in this case, we now have 4 over 52 times 3 over 51. Now we can reduce these fractions if we want to, before we multiply numerators and denominators. So this gives us 1 over 13 times, now 3 over 51 is actually not a bad fraction, it's 1 over 17, and that's going to give us 1 over 221. So 1 times 1 is 1, 13 times 17 is 221. Okay, let's keep going down the page and do a couple more. So in this one, we have a spinner with 5 equal sections colored red, blue, green, yellow, and white. So just in case, just to kind of give you the idea again, we have a spinner. Sorry about the evenness of it. We're going to say that this is exact. Okay. So each of these are the exact same thing. So this is the spinner. So one section is red, blue, green, yellow, and white. And then there's a little stick that spins around. So that's what it looks like. And then it says the spinner with 5 equal sections colored red, blue, green, yellow, and white is spun twice in a row. The first event is spinning red and the second event is spinning red as well. So are these independent or dependent events? Well, first of all, spinning red the second time doesn't matter. The red that was spun first has no effect on the red that is spun secondly. So this is independent events. Which means that we can use the independent formula, which says the probability of red then red again would equal the probability of, I'm so sorry about that, that's P, times the probability of red. And in this case, we have 1 over 5, because there's only one red out of the 5 choices, times 1 over 5 again. So no reds were taken away and the total number of colors didn't change. So in this case, we have 1 over 25. Okay, E, 2 marbles are drawn without replacement. Right away, we don't even have to read any further. Because they're not replaced, that tells us right away that the events are dependent. So there's a bag that has 7 red marbles and 3 blue marbles. The first event is drawing a red marble and the second event is drawing a blue. Now, because they're dependent, we have to use the dependency formula, which is the probability of red and blue is equal to the probability of red times the probability of blue, given that red has already occurred. So let's look at what we have here. Well, what about the red? Well, there were 7 red marbles in total. So we have 7 out of the total number of marbles is 7 plus 3, which is 10. So there we go. But now for the second one, we're taking that red marble and we're not putting it back. So our total marbles in the bag is now reduced to 9. Now, the blue marbles, however, they didn't change number. There's still only 3 of them. So it's 7 times 10 times 3 times 9, which now gives us 21 over 90. Now we could have reduced the 3 over 9 to make 1/3. We can reduce it this way as well, dividing top and bottom by 3. We get 7 over 30 in this case right here. Let's keep going. Now, using the following information, answer the next 3 questions. Now, Ronnie is going on a cruise. The brochure says that the probability of seeing a whale is 9/10 or 9 over 10, and the probability of seeing a seal is 3 over 5. What is the probability that Ronnie will see a whale and a seal? So basically, we're looking for what is the probability of whale and seal. Well, we're going to think, is this a dependent or independent event? Well, it's independent. One does not change the other, so we think. So let's look at it. So probability of the whale times the probability of the seal. So let's look at what we have here. The probability of the whale, well, we know that is 9 over 10. And the probability of the seal is 3 over 5. And that's going to give us 9 times 3 is 27 over 50. And that actually gives us a nice decimal. I'll show you. This one is a 0.54. And that would be B. Now, let's look at the next one here. What is the probability that Ronnie will not see either? Well, this means we need to know what the complement of each of these things are. So that, in other words, what is the probability that we do not see a whale? Well, if the probability of seeing one is 9 out of 10, that means the probability of not seeing one is 1 over 10. Likewise, with the seal, the probability of not seeing a seal equals 2 over 5. So now that we have these complements, we can say the probability of no whale and no seal equals the probability of no whale times the probability of no seal. So in this case, we have 1 over 10 times 2 over 5, which gives us 1 times 2 times 10 times 5, which is 2 over 50, but they're both even numbers. So we can reduce this down to 1 over 25. And as a decimal, we get 0.04. So we got A. Now the last one. What is the probability that Ronnie will see only one of these things? Okay. In other words, what is the probability that he'll see only a whale or he'll see only a seal? Now listen to the word I said. I said or. So in other words, we have to say, what is the probability of a whale and no seal, or the probability of no whale and a seal? Now, that or there, as I mentioned at the beginning, that means we need to add these cases. So we have 2 cases. So this is an example of cases, and we have to add these 2 cases together. So when we do that, we're going to say, what is the probability of a whale and a seal? Well, because they're independent events, we're going to say the probability of the whale is 9 over 10 times not a seal is 2 over 5 plus the probability of not a whale, which is 1 over 10, times the probability of a seal, which is 3 over 5. So remember that the ands are multiplies, the ors are adds. So in this case, I don't actually want to do any reducing first because I have this adding right here. I need to have a common denominator to add them. So I'm not going to reduce anything yet. So we're going to do all our reducing at the end. So I get 18, 9 times 2 over 50 plus 1 times 3 is 3 over 50. So notice by doing that, I kept my denominators the same, which is going to reduce the amount of work I have to do. So I get 21 over 50. And now putting that into the calculator, I get 0.42. And there we go. Now let's look at number 5. The probability of P of A and B equals this. So they're telling us what A and B are. And then they're telling us that the probability of A equals 0.78. So they're asking us to find what is the probability of B given A. So of course, these are dependent events and we have to use the dependent event formula. So we're just going to say the probability of A and B equals the probability of A times the probability of B times A, or B given A. And I want to really emphasize the importance of including the formulas. On any question, regardless of how simple it may seem, I really want students to show me the formula they're starting with. That way, there's no doubt in my mind when I'm looking at work what you're thinking. So now that I have this, I can do it two ways. I can go ahead and change around the formula by dividing both sides by the probability of A. It's okay to work with formulas. So that means these cancel, and I'm left with the probability of B given A equals the probability of A and B divided by the probability of A. So that gives us 0.725 divided by 0.78, which equals 0.92948, which if we're going to round, say, to two decimal places or the hundredths place, what we're going to normally do, we're going to put a little approximately sign because it's no longer equal if we're rounding. So we're going to say it's approximately equal to 0.93. I want you to make sure that if you are rounding things and that it's not an exact value when you're rounding, that it's not going to be an exact value when you're rounding. We want to show that you understand that it's approximately equal to and not equal to, okay? All right. Events A and B are independent. Okay, so we know which formula we need to use. They're saying that the probability of A equals 3 over 8 and the probability of B equals 5 over 8, and we're going to calculate the following. So the probability of A and B, again, write down your formula, practice how you play. So the probability of A times the probability of B. So probability of A is 3 over 8. Probability of B is 5 over 8, which means 3 times 8, 15. 15 over 64. Let's leave it like that because we can't divide anything here to reduce it down. 64 divided by 3. Yeah, doesn't work. So we're good. Now let's look at the next one. This one is the probability of A and not B. So that first means we need to figure out that it's not B. Well, if 5 over 8 is B, that means 3 over 8 is not B. And while we're at it, let's do the probability of not A because we're going to need that in a bit. So the probability of not A is 5/8. Now let's look at this one. And again, I know we don't like writing things out, but we're going to do it anyway. So that equals the probability of A times the probability of not B. That's going to give us 3/8 times not B. Well, that's 3/8 again. So that gives us 9/64. Now, the next one, well, let's just write our formula from this one. So the probability of not A times the probability of not B. Well, not A was 5/8. Not B was 3/8, which equals 5 times 3, which is 15/64. Now, I want to point out something with these two answers. You're probably like, wait, those two are the same. This one here is the same as this one here, and this one is not this. I want you to recall that these are not A and not B separately, which is very different than, for instance, the complement of A and B, like that. So if we think of this on a Venn diagram, so let me get my pen working there. Remember, this is probability of A and B. I'm going to get rid of that line, which is this little piece in here. That's A and B. If we were to wanted the complement of that little piece in the middle, that would be all of this here. That's all of that there, all not including that middle piece, like that, which is quite a big area. So if we were to find the probability of A and B, but not it, that would be all that. But this is actually the intersection of the complements, which is a little bit different. If we wanted to find the intersection of the complements separately, remember, if this is A and this is B, well, not A, let's do two different colors. Let's do the yellow. So not A, I don't know if that shows up very good. Let's use blue. This is not A, okay? Color it all in. But not B, let's see what's going to stand out. Let's do that one. Okay. But not B is that. So we are looking for the intersection of not B and not A, which is this kind of purpley color one here. Okay, so that's the overlap, which is much smaller than the green area over here. So note the difference between the two. That probability of not A and the probability and not B does not equal the probability of this. These are two separate things. So keep that in mind. So it's not, we can get them, they're exactly the same. Let's keep going. So the probability of A is 0.375 and the probability of B is 0.625. And the probability of A or B is 0.75. Find the probability of A given B has already occurred. Okay, well, if I wanted to do this question, I would first need to write down the fact that it's a dependency, so that the probability of B, and A equals the probability of B times the probability of A given B has already occurred. Well, I know my probability of B, but I don't know this piece right here. I don't know my probability of B and A. I've only been given the OR. Well, this brings us back to whether something is mutually exclusive or not. If it is not mutually exclusive, in other words, disjoint, the probability of A or B equals the probability of A minus the probability of B, plus the probability of B minus the probability of A and B. Remember, that's that overlapping area of the two parts of the Venn diagram, the A and B. And because they're overlapping, we have to subtract one of them away to get the correct probability of the OR. So in this case, we actually have to use the not mutually exclusive formula first in order to solve the first equation here for probability of A given B. So let's isolate this part right here. And we can do that by adding this to both sides. And after that, we're actually going to subtract away the OR. Now, if you prefer to put your numbers in first, that's okay. But I just want to show you something. This is going to give us the probability of A or B plus that. I'm actually going to subtract, let's see, let's put it like this. Like that. Okay. Now, if you've forgotten, we're going to subtract this part now. And we're going to do it from both sides. Okay. So what does that give us? Well, that basically, just to show you, if you ever have to find the probability of A and B in this formula, you're just going to substitute these two. So I just did the math just to show it again, and we're just going to substitute those two so that you're left with the probability of A and B, and we can actually just get rid of those so it's easier to see. I'll just write it over closer. So I am finding the probability of A and B because that's what I need to put over here. So probability of A, they give it to us as 0.375, plus the probability of B is 0.625, minus the probability of A or B, which is 0.75. Now, when we put all of that into the calculator, we get 0.25. So now we have the probability of A and B. We can go over here and substitute it in. Now, before I manipulated the formula, if you want to do that, go right ahead, or we can just put in the numbers and then manipulate. So I can say this is 0.25. The probability of B is 0.625 times the probability of A given B. And now we're going to divide both sides by 0.625. That means I got some canceling going on over here, so that the probability of A given B equals, putting that into the calculator, you're going to get a repeating decimal, which is 0.666 repeating. Now, rounding that to 2 decimal places is going to be approximately 0.67. So our final answer as a rounded decimal would be that. Now let's look at number 8. Given the Venn diagram, answer the following questions. What is the probability of A given B? So this telling us that these are dependent events. And because we're looking at the probability of A given B, that the probability of B and A equals the probability of B times the probability of A given B. Notice because the A was here, it's the second one, so that means B happened first. So that's why I wrote it B, then A. So putting in the things we know. Well, we know the intersection. The intersection is 0.2. So we're going to put 0.2 right there. And for the B, well, now the B is the entire circle right here. So it's everything right inside this circle here. So actually we have to add the 0.1 to the 0.2, and that's going to give us 0.3. And that's still probability of A given B. And we're going to divide both sides by 0.3. Which in this case, the probability of A given B, and that equals, well, it equals 2/3, or if you put it in our calculator, it is going to give us 0.66 repeating, or in other words, approximately 0.67. Now let's look at the next one. The next one is B with A already happening. So in other words, this way, notice our A's are first, equals the probability of A times the probability that B has happened given A has already happened. Okay, so the probability of A, well, the probability of A is 0.3 plus 0.2, which is 0.5. And just like in the first one, oops, pen's doing weird things. This one is still 0.2. It's still the intersection. So now we're dividing both sides by 0.5, which means the probability of B with A already happening is 0.2 over 5, which is 2/5, or putting it in the calculator is 0.4, and that's an exact decimal. Consider the two events such that the probability of A equals 0.3 and the probability of B equals 0.4 and the probability of A or B equals 0.5. And notice the options it gives us is we have to really determine, is the event dependent or independent and mutually exclusive or not mutually exclusive. Let's start with mutually exclusive first. We know that if events are mutually exclusive, we know that the probability of A or B equals the probability of A plus the probability of B. That's because if they're mutually exclusive, they're disjoint, they're not touching, which means there's no overlap and we don't have to subtract the intersection, because the intersection of these things, if they're mutually exclusive, is 0 because there's no intersection. So let's look and see what is the probability of A or B. Because we don't know if these things are equal, we're just going to go with our old left side, right side thing. Now the left side of this, which is the probability of A or B, is 0.58. Now the right side is A plus the probability of B, which is equal to 0.7. That means that these two events are actually not mutually exclusive. So that means we're choosing from B and D. So the next thing we have to determine is, are these independent or dependent events? So let's test for independence. It's the easier one to test for because we know for independent events, we know now that the probability of A and B equals the probability of A times the probability of B. Okay. However, we do not know the and statement here. But now that we know that this is not mutually exclusive, we can go over to our probability of A or B for mutually exclusive events, because remember, this is what it is. And we're going to rearrange this to solve for the and. And remember, we're just going to switch those two end pieces. So that it's going to become the probability of A and B equals the probability of A plus the probability of B minus the union of probability of A or B. And let's fill everything in. So we get 0.3 plus 0.4 minus 0.58. And that's going to equal, putting everything into the calculator, 0.12. So now we have that. So now let's do our little test. Because we don't know if they're equal yet, we're just going to look at right-hand side, left-hand side. So the left side, which is now the and or the intersection, is 0.12. The right side is 0.3 times 0.4, and look at that. Those things equal 0.12. So this is an independent, not mutually exclusive event. So our answer is D. Okay, let's look at number 10. Number 10, here we have a bunch of books on a shelf. We have 5 bio, 4 math, not enough math books in my opinion, and 7 history books, and they're randomly placed on the shelf. Louise selects 2 books, one after the other. Determine the probability that both books are on the same subject. Okay. First of all, he's taking books off the shelf, so we know that these are dependent events. You take one book off, that changes the number of books left on the shelf, so we need to kind of think about what is that denominator going to be of the second probability. However, there's another piece to this. It says the same subject. So that means we can have the probability that it was a bio and bio, or the probability of a math and then another math, or the probability it's a history and then another history. So look what we got here. We've actually created a formula with our words because remember, and represents that multiply and the or represents the adding. So let's do it like this. So the probability that we have the same subject of both books, that's going to equal, well, what's the probability first of the first book being a biology book? Well, there's 5 bio books. And how many books are on the shelf? Well, the total books equals 5 plus 4 plus 7, which equals 16. So we have 16 books in total on the shelf. And then we're going to multiply that by the probability of getting the next bio book. Well, in this case, numerator and denominator has changed because now there's only 4 bio books because we already taken one off. So there's 4. But the total books have also changed because we've only taken one off. So just to note, sometimes the second one does change as well, not all the time, depending on the situation. So now we have that first probability. Then we have the or. The or means we have to add whatever follows, which is the probability of math and then another math. Well, what is the probability if the first book we took off was math? Well, there was 4 math books to begin with, and then there was still 16. Because remember, we have to think of this as if we're doing it all over again, but considering the math. And then how many math books are left after we take that one off? There's 3, and there's still 15. And then we're going to add again, because now we're going to look at the history case. So really, this is 3 cases. Okay. So now the third case for history, there were 7 history books. Way too many history books. Oh, never mind. I like history. And 6 now, and then 15. Just like that. Okay, now remember, I don't want to do any reducing because I'm adding things and I want the denominators to be all the same. So when I do this, I actually get 20 over 240 plus 12 over 240 plus 42 over 240. So I have a probability for each case. Okay. Now putting those all together, do I have enough room here? I'll just keep going this way. And we're just going to add the numerator. So remember, adding fractions with a common denominator, the denominator stays the same. I add all the numbers at the top, 20 plus 12 plus 42, and that gives 74. Now that can be reduced. We got even top and bottom. That can be reduced to 37 over 120. And if we were asked to put it as a decimal, we could say that it was approximately equal to, rounding to 1 decimal place, 0.31. Now it's asking, are these events independent or dependent, and explain. Now remember that explain. You have to say it in words. So we already said that because there was no replacement of the first book, that these events are dependent. So we would say these are dependent events and we can say it in multiple ways, but let's say it so that it captures as much as possible. These are dependent events because not replacing the first book affected the probability of selecting the second book. And there we go. So remember, whenever you're asked to explain, it has to be words, not math. Okay, last page. So 2 cards are drawn from a standard deck of 52 cards. Determine the probability of the following events with replacement and without replacement. So let's look at them in 2 ways. So the first one is we're replacing the cards and we're asked, what is the probability of 2 reds? Okay, so the probability of red and red. Well, the probability of the first red, well, how many reds are in a deck of cards? Well, half the cards are red. Now you can write it as a half if you want, or you can say, well, there's 13 cards in each suit and 2 suits are red. So there's 26 cards out of the 52 that are red, like that. You can write it like that. Now we're replacing the card back. So when we want to pick another red card, the probability is the same. Now at this point, if you want, you can change it to 1/2 times 1/2 if you'd like, which is going to give you a quarter or 0.25. We can leave that like that. So this is with replacement. Okay. Now what about if we're not replacing it? Let's say we're doing this again, but we're not replacing the first card. Well, the first probability doesn't change because there's still 52 cards in the deck and there's still 26 reds. So it's 26 over 52. But now we've already picked a red out. And so that means there's now only 25 red cards left in the deck. Now, if we change the top, we got to change the bottom because we've removed a card. So that bottom is 51 as well. Now, if we're going to reduce this down, if we want, we can, reduce it down to say 1/2 times 25 over 51. It's a nice idea to get into the habit of working with the fraction. I realize the calculator can do it for you, but sometimes it's just even faster because look, 1/2. I multiply the numerators. I have 25. 51 times 2, well, that's 51 plus 51, which is 102, which there you go. We got that. Now, if we want to write that as a decimal rounded, it's going to be approximately 0.245. Not much difference, but those numbers are big. Notice it went from 26 over 52 to 25 over 51. So it's not really going to change the probability that much. Let's look at the next one. What is the probability? The first card is a king and the second card is a 5. So what we're doing, we're finding what is the probability of king and 5. Okay. Well, what's that probability of the king first? Well, the probability of the king is, there's 4 kings in a deck, so there's 4 over 52. We've replaced the card. So there is still, when we go to choose a 5, there's still 52 cards left, and there are 4 5s, one for each suit. So now we have 4 over 52. Now these reduce down nicely, because that reduces to 113 times 1 over 13, which is 1 over 169 as a fraction. Just get used to working in fractions. And then that is approximately equal to 0.0059. What about replacement? Okay. The probability that we have a king and then a 5 equals the probability of the king. I'm going to write out the formula. I realize I didn't do it there. Let's put that in just so, yeah. Let's do that. There we go. Now this one here, probability of a 5 given that the king has already been chosen. Okay, the probability of the king, 4 kings in deck, doesn't change the first probability. But it does change the second one because now there are only 51 cards in the deck. However, in this case, the second thing is not a king, it's a 5. So in this case, oops, I'm getting caught up in all the 5 business. There's still 4 5s in this. So the numerator didn't change for this because there's 4 5s. It's the denominator of the second one. So when we multiply these together, top and bottom, 4 times 4 is 16. I can never do 52 times 51 in my head, so I'm going to get the calculator to do it for me. And I get this. Now, when I do this, I can see they're both even numbers. That means they can be reduced. If I divide top and bottom by 4, I get 4 over 663 as a exact value. But if we want to round it down, we're going to say it's approximately equal to 0.006. Now, that comes from, it used to be 0.00603, but, that's a lot of decimals. So let's leave it at 0.006. Okay, let's go to the next one. Now, this one, we have to check the wording. It says one of the cards is a king and the other is a 5. That means there's 2 cases that we have to consider. Remember, when we have cases, we're going to have to add. So it can be, what is the probability of a king and then the 5? Or the probability of the 5, and then the king. And remember that or means add, the ands mean multiply. Well, let's do this. There is replacement here. So really, we're just saying what is the probability of the king, times probability of the 5 plus the probability of the king times the probability of the 5. Oh, let me fix those up just to be consistent. There we go. It really didn't matter in this case because there wasn't replacements, and it's these are independent of each other. So, but just for consistency. So the probability of the king is 4 over 52 times 4 over 52. So that's that. And then we're going to add it to itself again. Nothing's changed here. The probability of the 5 and the king are independent of each other because of the replacement. So we have this. So what we end up getting, really, this 4 over 52, we already know is 1 over 69, 169. So really, we got this, which is, as adding just the numerators, because we have these common denominators, is this. And if we want, we can make it into a decimal, and that's approximately equal to 0.01183. I do want to caution people about using rounded values at this point from previous steps. If we thought we could, take this and round it, just be careful that you are holding on to enough decimal places. Sometimes a rounded value, like notice we are just adding it to itself, 0.1 over 169 to itself. If I took the 0.0059 and added it to itself, in this case, I do get the same answer, but sometimes rounding kind of messes up and you might not get it. So you really want to make sure that you're holding on to enough decimal places when doing this. Now, with these cases in the dependent event, we do have to really kind of consider the order very carefully because k and 5, or what's the probability of 5 and k, it looks a little different, remember? So really, it's the probability of k times the probability of 5 given k has already happened. That's the first part. That's case 1. But then we have to add it to case 2, where it's the probability of 5 times the probability of the king given 5 has already happened. So that's what it looks mathy like. What's the probability of the king? Well, the probability of the king doesn't change at this part of the case, but this is going to be like the beginning. That's going to be like this one here. So it's 4 over 51 plus, so that's the first case. The second case, it actually tends to be the same thing because there's still only 4 5s. So numerically, it's the same. Not always the case, so make sure you're thinking and writing it out carefully. So we get this. Okay. Now that means really it's that doubled. So it's really 4 over 663 plus 4 over 663, which is 8 over 663, like that. And that is approximately equal to 0.0121, or let's just say 12. All right, number 13. No, sorry, number 12. There are 3 red marbles, 6 blue, and 5 green marbles. 2 marbles are drawn without replacement. What is the probability of a red and then a blue marble? Okay. So we're looking for the probability of red and then the blue. So that means we need to know what is the probability of the red, and it says without replacement. that means this is dependent, so we have to find what is the probability of the blue given that the red has already happened. In this case, we also need to know the total of the marbles, and that is 3 plus 6 plus 5, which is, see here, 3 plus 6 plus 5, we got 14. 14 marbles in total. So when we're looking at what is the probability of the red, we put in 3 red marbles over the total number of marbles, which is 14. Now, what about the blue? Well, the number of blue marbles hasn't changed, so the numerator is just going to be 6. But the denominator is going to change because we have taken a red marble out, and so that means we're left with 13 marbles left, and that means our probability is going to be 3 times 6, which is 18, over 14 times 13, which is 182. Now that can be reduced down as a fraction by dividing top and bottom by 2, which is 9 over 91. And that is approximately equal to, well, when we look at it, 0.098901. Now, just a point out here, if this asks you to round it to 2 decimal places, we look to the 8, and that means we have to round that number up to the next one. Well, the next number is 10, so that means when we're rounding that, it's actually going to be 0.10, okay? So we have to keep the 2 decimals, so because it's 10, we're going to put a 0 right there. Last one here, or second last one. An example of dependent events is drawing a white marble out of a container and drawing a what? Okay, so we have a container and we're picking out a white marble. They're saying, okay, the first option is we have a black marble out of another container. Okay, so we have 2 containers in this case. So we have 1 and then 2. Just like the spinner and the die that we were talking about at the beginning, these are 2 separate objects, and these things don't affect each other. So this thing here, these are independent events, so it is not A. The second one, it doesn't matter that they went back to white. We still have another container. So we take something out of that. We take something out of that. It doesn't matter that these 2 containers, it's still a white marble. They're still separate containers, still separate objects. So therefore, in this case, they don't affect each other. So it is also independent. The other one is another white marble out of the same container after replacing the first. Well, replacing tells us that it is also independent. So it is not this one as well. Therefore, we have one left, and just let's go over it anyways. A black marble out of the same container, but we haven't replaced the first one. Okay, so without replacing means these are dependent events, so our answer is D. Okay. A bag contains 4 black marbles and 5 red marbles. A marble is selected from the bag, replaced, and the second marble is selected. Determine the probability that both marbles were black or both marbles were red. Look, there's that or. That means we have 2 cases. The first case, probability is first one's black and then the second one is black. Notice here we have replacement, so these are independent events. And then because it's or, we have to do the or of the second case, which is the probability that it's red and then red. So both are red. Well, let's look at what we have. We need the probability of the black times the probability of the black plus the probability of the red times the probability of the red. That's a terrible time sign. Let's fix that. Okay, So the probability of the black, well, what is the total? There are 9 in total. So that's going to be our denominator. There were 4 black, but we put it back and then select it again. So there's still 4 black in the bag, and then there are 9 still in there. So we have that. The next one is the red. Well, there were 5 red to begin with. So remember, this is case 2. We've already done case 1. That's done. We're now considering case 2, and there's 5 there. We're thinking as if we're starting over, so there's still 9 there. However, we've put the marble back, so when we go ahead and check the second one, take the second one, we got 5 again, possibility, and then we still have 9. Again, we're not going to do any reducing here. It's not possible, but we wouldn't do it anyways because we want to have a common denominator. So 4 times 4 is 16, over 9 times 9 is 81, plus 5 times 5 is 25, over 9 times 9 is 81. And so got a common denominator, just going to add those numerators together, which gives us 41 over 81. And our answer is C. Now, this last question is missing a bit of information. It's asking us, determine the probability of B if we know this and this. Now, we could say, is this a dependent or independent event? If it were a dependent event, that must mean we're missing some information and we wouldn't be able to do it. So we're going to assume that this is an independent event. Okay, that's the only possible way we can do this question. So assuming independence, we're going to say that, going back to our independence formula, that the probability of A intersect B equals the probability of A times the probability of B. Now we can go ahead and rearrange the formula. It's okay to get in the habit of working with formulas. So we're going to do that, meaning that these things here cancel out. So we're left with the probability of B equals the probability of A intersect, B, just to write it out, all nice and neat. And that means we can fill in what we know, make our substitutions. It's okay to make the substitutions first and work with the numbers if that's what you're most comfortable with, just as long as you write down your formula. So we have 0.32 over 0.65, which is 0.492307. Now, be clear, this one actually gave us some restrictions here. We have to round to the nearest tenth. That must mean we have to take that 9 and look at the 4, which means this is approximately equal to 0.35. Well, that's the end of this lesson. If you have any questions, make sure you get in touch with your teacher. I hope you have a great rest of your day. Take care.